Hello everyone and welcome back to physics class. Today we are going to talk about Newton's laws. So Newton came up with 3 laws that we use every day in physics. The first one states that if there is no external resultant force acting on a body, then its acceleration is 0. So when we talk about Newton's first law, we often use the word inertia. Now, inertia is an object's tendency to keep its state of motion. Basically, if something is at rest and you don't have any external force acting on it, then that object is going to stay at rest. Similarly, if something is moving at a constant velocity and there's no external force acting on it, then that means that that object is going to continue moving at constant velocity. So let's take a look at an example of inertia. So here we have a bunch of people who are on the bus, and all of a sudden the bus stops. We see that all these people get thrown out of their seats, and that is because these people were moving at a certain velocity, and they didn't stop. It was the bus that stopped. Now, if they all had worn seatbelts, the seatbelts would have actually prevented them from falling over into the front seat in front of them. This is why we are told that we need to wear seatbelts when we're in a car. Because if we had to stop suddenly, you are moving and you are going to want to keep moving. There is nothing there that's going to stop you unless there is an external force acting on you. That external force is the seatbelt. The seatbelt is attached to the vehicle, and so that means that when the vehicle stops moving, then the seatbelt also stops moving, which then prevents you from flying forward. So let's take a look at another example. Let's do a little bit of a thought experiment here. So up here, we're all pretty familiar with snow and having it stuck on our boots and all that kind of stuff. So when you have your boot and you have a bunch of snow stuck to it, what do you tend to do to get rid of the snow? Well, typically we tend to stamp our feet, right? So we tend to lift our feet and push down and lift the feet and push down. This is actually using the concept of inertia. You see, the snow is kind of stuck to the boot, but it's not attached to the boot. So when you are stamping your feet, you are forcing your boot to stop moving, but the snow that is on the boot is going to continue moving because it wants to keep that state of motion. So the snow is going to fall off the boot whenever you stamp it on the ground. Now, of course, this depends on how sticky the snow is. If it's really sticky snow, you're going to have to stamp really hard to get it off. If it's fluffy snow, it's pretty easy to stamp off. Now, Newton's second law states that any resultant force can be described using its mass, the mass of the object, times the acceleration of the object. Because this is a formula here, this is one of the laws where we actually can have problems where we would have to calculate things. So let's go ahead and identify the steps to help us solve Newton's second law problems. Step number 1, we need to identify the body that is being analyzed, or the body that has the forces acting on it. Step 2 is we need to identify all the forces that are acting on the body. So basically draw a free body diagram. Step number 3 is you need to choose your x and y axes. And this is important because when you have inclined planes, that kind of rotates the x and y axes, so you have to make sure that you choose those. Step 4 is you write out your equations, and then of course you solve it. So let's take a look at an example of how we can solve a problem involving Newton's second law. So in this example, we have a 4-kilogram box that is being pushed along a frictionless surface. That means that there is no friction. So let's assume that this is ice. Ice is pretty low friction. It's being pushed with a force of 20 newtons. We want to know what is the object's acceleration. So draw our free body diagram of our box on a frictionless surface. We are assuming that it's being pushed to the right, so we have our force applied. There's no friction, so we don't have to worry about friction. And of course, we have the gravitational and the normal forces here, but we're not going to consider these. These two forces balance each other out. We're going to focus on this one right here. So Fr is our Fa essentially. So we're going to plug in our values and solve for our acceleration. So Fr is equal to mass times acceleration. Our applied force is the same thing as our Fr. So 20 is equal to 4, which is our mass, times acceleration. To isolate for acceleration, you're going to divide both sides by 4, and we're going to find that our acceleration is 5 meters per second squared. Let's take a look at another example. A 35-kilogram child is going down a slide at an angle of 25 degrees. Assuming there is no friction, what is the acceleration of the child? So let's go ahead and draw in a free body diagram. We have here 25 degrees. We have here our child, and we know that the child is being exposed to gravity, so Fg, and then the normal force. There is no friction, so we're not going to have any arrow indicating friction. However, we do need to break up our Fg into the Fgy and the Fgx forces. Now, in this case, we are not going to look at our normal force or the Fgy. We're going to look at the force that is pulling the child down the slide, and that is Fgx right there. So, first thing we need to do is find what our Fg is. So Fg is equal to mass times gravity, so 35 times negative 9.81, and that will give us negative 343.4 newtons. From here, we would use Fgx is equal to Fg sine theta to find what our resultant force is. So, negative 343.4 times the sine of 25, and that will give us negative 145.1 newtons. So this is our resultant force right here. That's acting on the child, causing it to slide down the slide. So now we're going to use Newton's second law to find what our acceleration is. So negative 145.1 is equal to 35 times a. We're going to divide both sides by 35, and we find out that our acceleration is negative 4.15 meters per second squared. And that is the acceleration of the child. Now, the last of Newton's laws states that if body A exerts a force on body B, then body B exerts a force equal and opposite to the force from A. This can be a little confusing, but ultimately we end up with this formula here. Fa is equal to negative Fb. And we've actually already seen this formula. Take a look at a box that is just resting on a table. We know that gravity is pulling down, And we know that the normal force is pushing up, right? What is the formula for the normal force? Well, the normal force is equal to the negative of the gravitational force. Doesn't this kind of look familiar? Yeah. So that is something that we've already kind of seen before, but let me describe it to you using a new example. Let's say that I have two cars here, and they have both hit each other in a head-on collision. This is car A. This is car B. Car A exerts a force on the car B, and car B exerts a force that is equal but opposite in direction to force A. Here I've drawn two circles that will represent black holes. Black hole A is half the size of black hole B. Which black hole will exert the greater force of attraction towards each other? These two are gravitating towards each other, so which one is going to exert the greatest force? Well, this is a kind of a trick question, because according to Newton's third law, they will both give the same force, just in opposite directions. So there is no greater force here. Sure, this is a greater mass, but we know from Newton's second law that F is equal to mass times acceleration. This law states that both of these forces are equal to each other, just in different directions. So it's not the force that is going to be greater than, it's going to be the acceleration. Since the mass is different, the forces are the same, your acceleration is also going to have to be different. So black hole A is going to accelerate faster towards black hole B than black hole B is going to accelerate towards A. I hope that that wasn't too confusing, but just know that even though there's different masses, there are different sizes, they still exert the same force on each other. Just one is going to be negative. Thank you for listening, and I will see you all next time. Bye!